All right, so I will continue on the third lecture on collective neutrino oscillations. And we have been talking about the introduction and overview in the first lecture. And in the second lecture, I give you some back-of-the-envelope estimates, not even calculations. So to make sure that our results are not that bizarre. And I just started giving you some tools that you can understand the calculations. And in the end of this lecture, I will show you some new development and the challenges. So you probably are not that interested in collective neutrino oscillation or neutrino oscillations, but why we are doing this. So through those three lectures, I basically want to tell you my philosophy about the numerical calculations. You probably one day will face my dilemma. So what is the dilemma? The dilemma for numerical calculation is once you write a code, you spend your time, you write your code and try to find out all the bugs and produce some results. Now, if the results are just as what you expected, great. You have done the right job, the code is right. But it's also frustrating because you are not discovering anything new. If you produce something really interesting, like what we have seen, it's bad in the sense that you don't understand what's going on, but it's also good, it's exciting, something new. But it could be just some numerical artifact, some beautiful numerical artifact. How would you know? And by presenting how we go through the analysis of the numerical calculations, we don't really fully understand the numerical calculation because it's too complicated. It's a very nonlinear problem. But just show you how we do this. We just go through the back-of-the-envelope estimates and then some of the simple models, and then understand that our calculations are actually correct, at least qualitatively correct. And then, of course, there will be independent groups doing similar calculations and numerically verify that those results are correct. All right, just briefly, what we have learned about supernova neutrinos. This is among the most energetic events in the universe. 10 to 53 ergs of energy, 99% of them carried away by 10 to 58 neutrinos. And in about 10 seconds, and you get neutrino species of 10 to 30 MeV or so. And then they dominate the energetics, influence nuclear synthesis. And what we really are interested about are the electron-flavored neutrinos, the anti-neutrinos, because they deposit energies into the matter, and also they flip a neutron to proton and backward. So when we put the neutrino oscillations in there, the problem becomes very complicated because of the Hamiltonian. You have three terms: the vacuum oscillation term, the matter term, and the neutrino self-coupling term. Once you put that term in, I try to explain to you that once you put that term in, the problem becomes highly complicated because of the flavor evolution of neutrinos emitted from every point on the sphere in different directions with different flavors. They can all become somehow coupled, and we don't really know how to solve that full problem, even if we just assume there's no hard scattering outside the neutrino sphere. So what we did was we do a simplification. We use a 1+2D model with the one spatial dimension and the two momentum dimension. So we assume there's a spherical symmetry on the neutrino sphere and also for the whole supernova environment. And then along any radial direction, we assume there's the azimuthal symmetry about that radial direction. And also there's a 1+1D, so single angle approximation, which assume that the flavor evolution of neutrino is completely independent of neutrino trajectories. We know that this approximation is equivalent to an expanding homogeneous gas away from the neutron star. But we know it doesn't really capture the the supernova environment because it's not homogeneous or isotropic. So we do the calculation for the multi-angle, and we got this picture. Especially for the neutrino sector, you see there are spectral swaps. Those are the neutrino survival probability. Looks like a step function as a function of energy, 1 here and 0 here. But for the neural mass hierarchy, it's the opposite. So they look like a mirror image of each other. This is for multi-angle calculation. And for the single angle calculation, you got a similar picture. Even if you use a different neutrino luminosities, you'll get a similar picture. So how do we understand that? Well, last lecture I told you you can just stare at the equations and just estimate the energy scale of those 3 quantities, compare them, you kind of get an idea where interesting things might happen. It doesn't guarantee interesting things will happen, but it probably should be something you should do before you actually run the numerical calculation or even writing the code. But this is actually not what we did. This is probably among the last thing what we did, because it's, as I try to run through those comparisons with you, you see there are many fine details. It's not that straightforward. But anyway, we think we kind of know some information about that here, and then try to really understand the qualitative behavior like the spectral split or swaps. We have to use more sophisticated models, not just by staring. So again, about that vacuum oscillation, we know that what happens because the neutrino mass eigenstates are not the same as their flavor states. And as a 2-flavor approximation, you've got 2-component system, and we know that the 2-component system is equivalent to a spin half particle, just spin up and spin down. And that's equivalent to the quantum mechanical system. And then the Hamiltonian can be expanded expressed in terms of the Pauli matrices. So what we did, what we can do is we group the neutrinos in different flavors into flavor isospins. And we define the flavor isospin as the expectation value of the Pauli matrices with respect to the neutrino flavor wave functions. And the equation of motion, we can translate that into the equation of motion of the flavor isospin. And for vacuum oscillations, what you have is a vacuum field which is not in the z direction. And then the flavor isospin, if neutrino is initially produced as an electron flavor neutrino, will be in the z direction, but not aligned with the vacuum field. So that will precess around it. And once you project that precession motion onto the z-axis, what you get is this oscillation amplitude. And that actually is just the survival probability shifted by half. So that you get the idea where the neutrino oscillation comes from. Now, what about the matter effect? So for matter effect, you get this Hamiltonian with the only change you get is you add the matter term on the diagonal elements. So what happens there is, if you, again, in this flavor isospin picture, what you have, you add another effective field which is the same for all neutrinos, for all the flavor isospins, because this electron is in the flavor state. So it's along the z-axis. Then the neutrino, the flavor isospin, will precess about the total field, which is given by this red vector. All right, so your neutrino is produced along the z-axis. The total effective field is in this direction. And then the neutrino flavor isospin will precess over there. And then as the matter density decreases, the green vector will decrease, will shrink, and then the red vector will rotate up to the blue vector, and this is what you get, because the flavor isospin will follow the direction of that total effective field. And here is an animation for the neutrino flavor isospin. So the dots on the sphere represent the direction of the neutrino flavor isospin with the different energies. The energy is given here, color-coded as a 1 over neutrino energy. And the reddish dots represent neutrinos, and the bluish dots represent antineutrinos. So for this particular calculation, I use the inverted mass hierarchy, and you see the antineutrinos will just move from the north pole to the south pole. That represent the flavor transformation, but the neutrinos will just stay at the north pole, so there's no flavor oscillation for neutrinos. And that's a vector. This is a spin picture for MSW flavor transformation. Now, how about the collective oscillations? Well, for collective oscillations, we have done many simplifications down to 1 plus 2D, and we even down to 1 plus 1D, but that's not good enough. It's still very hard to understand. So what we did was we looked at a homogeneous isotropic neutrino gas equivalent to single angle approximation, and we only put 2 neutrinos in there, actually 1 neutrino and 1 antineutrino with the same energy. So that's very simplistic system, and it's not just 2 neutrinos, it's a 2 neutrino species with some energies and densities. So when you do that, they are represented by the flavor isospins in the opposite direction, and we call that a bipolar system. And when you write down the equation of motion, what you found out is that equation of motion is equivalent to a pendulum in the classical mechanics. That's kind of interesting. The weight of that pendulum is inversely proportional to the neutrino number density. All right. So if the neutrino and antineutrino number density are equal, what you have is just a pendulum swing up and down, and we know that the change of orientation of the flavor isospin represents the flavor transformation, so that the swing motion of the flavor pendulum in the flavor space represents the flavor transformation. So that's collective oscillation. If you have unequal number of neutrinos and antineutrinos, then the difference actually give you a spin. So this is that the pendulum has an internal spin. You probably have all played with the spin tops and that kind of toy. So what you will have is that because of the angular conservation of angular momentum, that spin top will have the precession about the z-axis and up and down nutations. I won't go into the details of that because really the gyroscopic pendulum is a very complicated classical model. But just to give you a picture how to visualize neutrino oscillations. All right, so if you have played with that, the spinning top, you know when the spinning very fast and release from the upright direction, it will not fall down immediately because of the conservation of angular momentum. And that can happen for the neutrino system. So if you have an inverted neutrino mass hierarchy and with the very high neutrino number density, the very high neutrino number density corresponds to a very weak gravitational field, and you have a spinning top, so it will stay there. It's called a sleeping top. But when the neutrino number density goes down because the gas is expanding as the neutrino gas leave the supernova, leave the neutron star, the weight will increases. The weight of that pendulum will increase, and that will pull down the pendulum. And when the pendulum is pulled down, it actually not only just go down directly, but also start to nutation. and precession. And you can do that because that's just a two neutrino system. And you can do that calculation in Mathematica, for example. And this is what we got. You see there is a oscillation. This oscillation represents the precession, the nutation motion, actually. And the thick lines represent the case where the neutrino number density decreases so slowly that, or essentially have a sleeping top, you increase the weight very slowly. The top is still precessing with almost no nutation. So that's the adiabatic limit case. And then for the normal neutrino mass hierarchy, what you find out is the pendulum will start from almost the lowest position if the mixing angle is very small. And then you will not have much swing motion. That means you will not have much neutrino flavor transformation in that case, except when you go through MSW, because you know what the MSW effect does is to change neutrino flavors through matter effect. And that will raise the pendulum to the higher position. And then as the neutrino number density goes down, it will start that swing motion. And that's kind of what we have seen. Naively, you would think that just a very simplistic picture with homogeneous gas with just two neutrino, one neutrino and one antineutrino. How would that possibly represent a physical case? But indeed, when you compare that with our multi-angle, multi-energy calculation, this is what we see. The horizontal axis is the radius in kilometers. The vertical axis is the neutrino survival probability. And that's for the normal neutrino mass hierarchy case. So this dashed two dashed curves give you two limits when you have MSW flavor transformation. And what you see here is the flavor transformation really start within those two limits. So it's indeed is triggered by the matter effect, by MSW flavor transformation, as we have seen over here. So it's the MSW that actually triggered the collective oscillations, and after MSW happens, you have collective oscillation. So this part is a collective oscillation. And this is for the normal neutrino mass hierarchy, and you can see the MSW for this case occurs around 80 kilometers or so. But for the inverted mass hierarchy, it's a different story because it occurs at a much smaller radius, probably around 60 kilometers. So it's not triggered by MSW. And we know that for this case, in the inverted mass hierarchy case, you will not see MSW for the neutrino sector. So it's purely due to the collective oscillation. And so here in this region, what we have observed is that the sleeping top, that spinning top, is in upright position, but the weight is too light. So it's not enough to pull it down. So it's a sleeping top in upright position. And then when the neutrino number density goes down, the weight increases, you pull down that sleeping top, and you start collective oscillations. All right, so that's just the two energy beams, one for neutrino and one for antineutrino. Now we can put more neutrino energy beam in there, and this is the equation of motion for flavor isospins. S is the flavor isospin, and H is the total effective field. Has three components: the vacuum, the matter, and the neutrino-neutrino coupling. So for the vacuum oscillation, it depends on neutrino energy. So there's a dispersion of that term in terms of energy. So that term will tend to disrupt collective oscillations. If there's no neutrino-neutrino forward scattering, if there's no coupling between the flavor isospin, those flavor isospins will precess with different frequencies. And the neutrinos and antineutrinos, they will precess with opposite directions. So if there's only vacuum oscillation, there will be no collective oscillation for sure. And for the matter term, what you see here is independent of neutrino energy. It's the same for everybody. So it can be ignored, at least for this case, for collective oscillations. So suppose we ignore that term. And then the last term is neutrino-neutrino forward scattering. If you write it down in terms of the Flavor isospin, there really is just a spin-spin coupling. And you can write it down in this term. The is proportional to the total average Flavor isospin. And then the coupling strength is proportional to the total neutrino number density and with the minus sign, which tells you the coupling is not ferromagnetic, but it's anti-ferromagnetic. And also one thing you observe here is now you have basically a spin gas. It's in the flavor space. Those spins are in the flavor space. You have a spin gas. They are all coupled to each other, and they feel some external field given by this vacuum field. And although the strength of the vacuum field felt by different Flavor isospins, they are different, they are all in the same direction. So what does that tell you? It tells you that the equation of motion has a symmetry because there's only one external direction. So the equation of motion has a rotational symmetry about that z-axis, or actually about the vacuum field. So there's a rotation symmetry. Doesn't mean the solution will be axiosymmetric, but the equation of motion has that symmetry, and that can imply a collective precession mode about that symmetric axis. And if all the Flavor isospin precess about that symmetric axis, and that will generate a kind of a rotational magnetic field. It's not the real magnetic field, but it's kind of like effective field felt by the individual Flavor isospins. And if you have heard about the magnetic spin resonance, that will flip the Flavor isospin in the opposite direction. So that's kind of the idea behind this collective neutrino flavor transformation. So this is another cartoon animation, and Alex have shown a different version of it. So this is similar to the one I just showed, with one difference. The difference is that now I put the coupling between the Flavor isospins, or I put the neutrino-neutrino forward scattering in. And again, the reddish colors are for neutrinos, and blue colors are for antineutrinos. And now you see the dots will not just move one by one from North Pole to the South Pole, but rather they will kind of have a collective motion. And this collective motion are peculiar. This is a rubber band motion, stretch and collapse. But there's also obviously the precession about the z-axis, the common axis. So there is such a collective motion in there. And of course, this is a single angle calculation for homogeneous neutrino gas. What about the multi-angle calculation? For multi-angle calculation, we can plot the x-axis, the x component of the Flavor isospin, and this is for the radial trajectory with the different energies. And you can see that they all oscillate in phase. So only for one trajectory, but with different energies, they all oscillate in phase. So this is a collective motion. And what about different trajectories? If I look at the different neutrino trajectories, but for each trajectory, I average over the Flavor isospins. And again, they oscillate in phase. So this is indeed show you that there's a such a collective precession motion in the xy plane. Now, what does that imply? Now, suppose we have a pure precession mode. That means all the flavor isospin precess about a common axis, that the vacuum field, with the same frequency. That's what defines a collective precession, a pure precession mode. In that case, this is what you have. This red vector is the total flavor isospin is precessing about the z-axis or the vacuum axis, and then the individual flavor isospin is this orange vector. But this is not a very good way to look at it because everything is precessing. So what about if I go to a rotating frame, a frame that co-rotating with the flavor isospins, so that in this frame, the flavor isospin is static. And actually, everything should be static because my assumption is all the spins are precessing about the axis with the same frequency. So if I go to that rotating frame, everything is static. And we know the equation of motion tells me that the flavor isospin should be precessing about its total effective field. In order for the flavor isospin, that orange vector, to be static, the total effective field in such a co-rotating frame must be in the same direction or the opposite direction as that vector. So this is the total effective field, the black vector in the co-rotating frame that has to be aligned with that orange vector, the flavor isospin itself. So that's really important. But you see, because I'm going from a static frame to a co-rotating frame, I have to add a pseudo field here. This is just like, this is because my rotating frame is a non-inertial frame. If you have it in classical mechanics, when you go from a inertial frame to a non-inertial frame, for example, with acceleration, you have to calculate the physical system in that non-inertial frame, you have to add a pseudo force. And this is a similar case. If I go from a static frame to a co-rotating frame, I have to add a pseudo field. This is of order minus omega PR. So omega PR is the collective precession frequency. All right, so now I have a question. What will happen if my ansatz hold all the flavor isospins precess about the common axis or z-axis with the same frequency? What will happen if the neutrino number density goes to 0? Which direction should the flavor isospin be? Right, so if you look at here, the idea is, this is in the co-rotating frame, the flavor isospin has to be aligned with the total effective field, which has 3 components. One is the vacuum component shown by this green vector. One is the neutrino, the effective field from all the flavor isospins given by the red vector. And then there's also this pseudo field. So when the neutrino number density goes to 0, what direction should the flavor isospin be? Yeah, it will be aligned with the magnetic field, but is it arbitrary? What will be the magnetic field be when the neutrino number density goes to 0? Along Z. Must be along Z, right? There's no way around. Has to be along Z because the neutrino number density goes to 0. So all you have is the vacuum field, all right? But you see there's a peculiar thing here. This effective field is not just the frequency, the vacuum frequency anymore. It's a vacuum frequency minus the common precession frequency. So what that tells you is that this alignment is a kind of a step function. All right. So if your omega, if your oscillation frequency is larger than this, you are aligned with the, you'll be aligned, you'll be in the negative z-axis. If your oscillation frequency is smaller than the common precession frequency, the flavor isospin will be in the opposite direction. In other words, what you have is a neutrino self-probability to show up as the step function of neutrino energies, and I combine the neutrino energy, I write down this neutrino energy in terms of the oscillation frequencies. So for the inverted neutrino mass hierarchy, the mass squares difference is negative, so negative oscillation frequency corresponds to antineutrinos, and the positive oscillation frequency, negative oscillation frequency corresponds to neutrinos. So here you have a step function. And for the normal neutrino mass hierarchy, it's similar, except that now the mass square difference is a positive. So the oscillation frequency is a positive for neutrinos. You still have a step. It's over in the neutrino sector for the spectral we have used, but it will show up as a mirror image of each other, as we have seen over here. All right, so that's kind of explain the peculiar behavior of what we have seen over here. And in case you don't want to do such a complicated multi-angle calculations, you just want to know where the collective oscillation began. And there is a linear stability analysis method you can use. The idea is very simple. So what we have looked at is the flavor isospin, or you can just translate that into the flavor density matrix. You can construct that from the wave function, flavor wave function of the neutrino, and you make the assumption that you know on the neutrino sphere, the neutrinos are in the flavor space, are in their flavor states. So basically, you only have the diagonal elements. The off-diagonal elements are almost zero. So make the assumption the off-diagonal elements are very small. You only keep the linear terms of those off-diagonal elements. You write it, off-diagonal element is as big as x minus I as y. And you can write down the equation of motion for that off-diagonal element when it's very small. And also you make the assumption that you have a pure precession solution. For pure precession solution in this case, that means your off-diagonal element is proportional to this e to the minus I times the common precession frequency times t. When you do that, but this common precession frequency doesn't have to be real. It can be imaginary. If it is imaginary, that means you can have exponential growth, and that's exactly what you see over here. So whether you have a single angle calculation or multi-angle calculation, when the flavor oscillation begins, when collective oscillation just begin, you got the flavor instability. This amplitude will just grow exponentially. So it had the same origin as that collective precession mode. So in the last 10-20 minutes, I will just tell you some of the new developments. So one thing, so all the calculations, what we have done in multi-angle calculation, we actually use a lot of angle beams. This is something Tony was worried about, because in his calculation, he only have of order 100 of angle zones. And in our calculation, we use like 1,000. And in some other groups, use a calculation of 10,000. It's a huge calculation, I mean, in terms of angle beams. But why do we need so many angle beams? Actually, when we look at that problem, this problem has troubled us from the very beginning. And what the difficulty is, if we do not have enough angle beams, there will be some some artificial collective oscillations will begin at a very small radius. And the reason is that if you do not have enough angle beams, the solution of that discretized equation of motion and the equation of motion in the continuous angle beam limit, those two solutions are qualitatively different. So that caused a big problem. And recently, Shashank, who sits in the audience, he developed this moment method. So what we did here, we expand the wave function or the density matrices in terms of the multiples, in terms of Lagrange polynomials. And this is one of the examples. So this is actually correspond to the first calculation of what I have done. And now you see, again, the dashed curves are the initial energy spectra, and the cyan curve is the calculation if you use just the 10 multiples. You kind of already get some qualitative right behavior. With 25 moments, this is a green curve you get, which is actually the same as I get from, say, 1,000 angle beams. So just with the 25 moments. And that's a huge improvement. So that might be the way to go in the future in our calculations. And there are also many challenges in this field. For example, JJ, also in the audience, he found out this Neutrino Halo problem. So what this problem is, in our calculation, we have assumed the neutrinos have no hard scattering outside the neutrino sphere. But in principle, you could still have neutrino propagating here and then being scattered by a particle and then come over here. The chance is very low outside the neutrino sphere. However, the angle, the neutrino forward scattering Hamiltonian has this angle dependence. This angle is very large. So that turns out will compensate for its smallness. For example, this is what also JJ plotted out. The matter density got from Tony's simulation. This is the matter density as a function of a radius. And then you calculate the value or estimate the magnitude of the contribution from the halo neutrinos, which are not the halo neutrino corresponding to those neutrinos, and the core neutrinos corresponding to the neutrino directly emitted from the neutrino sphere. Then you compare the contribution from the halo neutrino to that from the core neutrinos, and this is the correction you get as a function of a radius. So it definitely is very large, especially at the larger radius. And that actually breaks our current computing paradigm. We really need to find a different way to solve the problem. In our calculation, we treat the problem as an initial condition problem. We evolve the neutrino beams as a function of radius. It's different from what supernova people do things. But here, if we consider neutrinos to propagate forward and then backward, we cannot really treat it as an initial condition problem anymore. So we probably have to do radiation high transport like supernova people do. And then there's an even more severe problem. So we all know that a symmetry in the equation of motion does not guarantee the solution will be symmetric, just as you know about the standard model, how the particles get met, where the Higgs particle come about. If the potential is like a Maxwell hat, and the ground, there's no just one ground state. There's a degenerate of a ground state. So the solution of the system, or the ground state of the solution, the ground state of the system is not symmetric about the axis of that Maxwell hat potential. So here is similar. What we have, the symmetry we're referring to is in our 1 plus 2D neutrino bulk model, we'll assume along any radial direction there is a axial symmetry about that phi direction. This is the symmetry I'm referring to. And even more interesting is, suppose I have approximate symmetry. The system is approximately axiosymmetric about the radial direction. But if the system becomes unstable, there's still no guarantee that this symmetry will be maintained. And actually, Raphael et al. And Mirici, the Raphael et al. First point this out. What they have done is do a linear stability analysis in this 1 plus 3D. So they assume a spherical supernova environment, and they assume the initial conditions are approximately axiosymmetric about the radial direction, and then they do the linear stability analysis. And what they found out is, in the end, there can be the flavor evolution of the neutrino can have this phi dependence. In other words, we cannot really ignore this phi angle as we did in the 1 plus 2D model. So how can we understand that? That actually is quite understandable if you look at the Hamiltonian itself. In the Hamiltonian itself, it has this geometric factor, as you recall, 1 minus p dot p prime, and the p is the momentum. Actually, should have a hat on there. The p hat is the momentum direction of the neutrino we are looking at, and the p hat prime is the momentum direction of the background neutrino. You can just rewrite it in terms of the spherical harmonics. All right, so the 1 is just the 1, 0, the monopole coupled to monopole. P dot p prime is dipole coupled to dipole. Of course, you include there are 3 dipoles. But you then divide it by 3. All right, and for a homogeneous gas, you can do this linear stability analysis again. And what you find out is that in that linear regime, all the multipoles are actually decoupled. So they will all evolve independently. But now if you look at the couplings, the monopoles are coupled just as what we have before. If you ignore that the p dot p prime, if you average that to 0. So this monopole mode is actually what we have discussed for the homogeneous neutrino gas. All right, so it's unstable in the inverted mass hierarchy case, but it's stable in the normal mass hierarchy case. But now you see there's also dipole coupling from the p dot p prime. That dipole coupling had a different sign as the monopole coupling. And translate into this collective oscillation language, it means those dipoles are unstable in the opposite neutrino mass hierarchy. And with the different coupling strength, that translates into they will become unstable at a different neutrino number density. And also for the higher multiples, they don't show up here. So they are not coupled to those instabilities. So they will be stable, at least in the linear regime. And you can do such a calculation numerically for the homogeneous gas. So this is for the inverted neutrino mass hierarchy, and orange line shows the amplitude of the monopole, and you can see they all start from very small random perturbations, very tiny. The amplitude you see is of order 10 to the minus 7, and only the monopole will grow exponentially, and all other multipoles will just oscillate. They will not grow in this linear regime. If you go to the normal neutrino mass hierarchy, the orange curve, that the monopole mode is stable, but that 3 dipole modes will grow exponentially. And what does that mean for supernova neutrinos? So for supernova neutrinos, that means collective oscillations can occur in either neutrino mass hierarchy. So previously, I mentioned that for the normal neutrino mass hierarchy, if you want collective oscillation, you have to pass through matter MSW, the matter resonance, MSW resonance. But usually for supernova, it doesn't really happen before collective oscillation, especially unless in some special cases. So, but here what this means is, even though the matter density can be large, so you do not have MSW resonance, you can still have collective oscillations in both mass hierarchies. And oscillation actually will occur deeper if you have a normal neutrino mass hierarchy. That's because the coupling between those dipoles are weaker than that of the monopoles. And also the angle-dependent modes, so for the supernova case, of course, for supernova it becomes more complicated. And what you can do, you can expand in the M modes. So along the radial direction, if your M equals plus minus 1 modes become unstable, you'll definitely develop a phi dependence. So that phi dependence will break the axial symmetry. And then if you think about it, if at this point, at a certain point, you break the axial symmetry, and you immediately also break the spherical symmetry. So the whole idea of this spherical model will break down, and that means we really need a new paradigm. All right, so I will come to my conclusion of those 3 lectures. So basically, for you, most of you, the take-home message is neutrinos really offer a unique and direct probe into the centers of stars, including supernovae. And that, of course, is because neutrinos coupled very weakly to the matter. So they can decouple at a very high density regime and carry the information from the core of a stellar object. And also neutrinos are really essential to supernova because especially the electron-flavored neutrinos and antineutrinos, and they deposit energy, they change the neutron to proton ratio, etc. And also we have this collective neutrino oscillation phenomenon. If that really exists, think about it. It's a collective quantum phenomenon on the scale of 10 kilometers. And Baha Balantakin have made this comparison to what the nuclear physicists study. So for nuclear physicists, you study nuclei and of a dimension Fermi, 10 to the minus 15, and with tens of nucleons. This is the collective phenomenon nuclear physicists study. For condensed matters, you probably study on the matter of order, say, centimeters, and with 10 to 23 particles. But for collective neutrino oscillations, you are talking about purely weak interaction, 10 to 50 some neutrinos, and on the scale of 10 to 100 kilometers. So it's a very different idea, different scale. And really what I want to tell you is my philosophy about numerical calculations. And of course, the question you can ask yourself is, how do you want to do your own calculations? If you have found out something new, what do you want to do about it? All right.
Enough number of angular bins, then you can generate some artificial collective effects just from discretization,
right?
Right. So then how do you know when the number of angular bins is sufficient? For example, how do you know if 1,000 bins is enough or 10,000 is enough?
We just increase number of bins until we achieve convergence. This is what we did in the beginning. But you see, what This is something I actually worry about the supernova simulations, because their calculation is so huge, they use so much resources, they cannot do this convergence test.
So I was wondering if you could compare the width of an angular bin with some natural scale in the supernova, and that way determine whether the resolution is sufficient.
No, this convergence is not from, I wouldn't say it's not from the, it's really from that equation of motion. Once you discretize the bins, the solution of that discretized equation of motion and the previous equation of motion, they are different. So it's not from the observation point of view whether you need that angular resolution.
Could you show the comparison with the moment method? So I just want to see, you talked about 25 moment equations are sufficient to reproduce the multi-angle simulation results. You also get one about 200. So that curve is identical with 25.
Right.
None of these, right?
Yeah, just to show the convergence.
Okay.
With 25, you already achieve convergence compared to 1,000 angle bins.
And in terms of the computational efforts, the 25 one, how much effort do you save compared to the regular?
It's hard to tell. Maybe Xiaxian can answer more, but what my understanding is, he just write a prototype code. So it's not, it doesn't, he didn't try to optimize the code that much.
But
Right.
even with the rough estimate at this point, you didn't put too much thinking into it. How much effort is already saved?
If you just, so there are two things. One thing is, if you say, I'm solving just the equation of motion. Now, previously I solved 1,000 partial differential equations simultaneously. Now I solve 25 simultaneously. So that's probably a saving of by how much? 440. And there's another thing is, numerically you can find out is you only need 2 moments before the collective oscillation begin. If you just use a monopole, just 1 moment, that corresponds to single angle calculation, we know sometimes it will produce the wrong result. But if you just use 2 moments, and then when the first moment, the dipole become significant, you can add other moments adaptively. So this scheme can be adaptive. It's not like the angle beam method. If you want to refine the angle beam, you have to add the beam in the middle. But in the moments method, you just expand it.
Very good. The other thing is that the stability analysis that you carried out really is sensitive to only the first 2 moments, right? So because in Hamiltonian, only two modes came in, basically.
That's actually not true.
Okay.
So what happens is that if you plot all the moments, let me just show you what that looks like. So what you see here, all the moments actually will grow exponentially. So that can also be found out when you try to use a linear stability analysis in the moment basis. But numerically, you see, you have some numerical noise over here. So the higher moments won't be important until they break the numerical, the noise threshold. So that's why, that's my understanding why you only need the first 2 moments in the beginning.
I just have a question about what you mean when you say moments, or when you have that calculation where you only use 25 moments.
Right.
Those would be L multiples?
Yeah.
Or L and M multiples?
This is in the neutrino Bob model, so there's only L, there's no M. the reason we have, so of course using an M will make things more complicated, but at the same time, we are not sure that that 1+3D model really make any physical sense.
Huaiyu, thank you very much for very nice lectures over the past few days.
Thank you.